Despite its name, AutoGluon is not just for Gluon or MXNet models. We already saw in the Tabular prediction module that AutoGluon had integrated many third-party libraries like LightGBM or CatBoost. Here we demonstrate how AutoGluon's hyperparameter optimization methods can help you tune various pieces of your own non-AutoGluon, non-MXNet models. As an example, we consider a PyTorch model for classifying images from the famous MNIST handwritten digit dataset. To run the second half of this tutorial, you'll need to make sure to have installed PyTorch. We first explain some of the search spaces supported by AutoGluon. These include simple spaces and nested search spaces. Each search space describes the set of possible values for a hyperparameter from which the searcher will try training models with particular values during hyperparameter optimization. AutoGluon also enables search spaces inside user-defined objects using certain decorators, and you can also decorate functions to automatically make them tunable. Basically, all you have to do is add one decorator to your existing code and it becomes tunable by AutoGluon Searcher and Scheduler. Let's start by importing AutoGluon. Now let's look at what an integer search space might look like. Here we can just specify an upper and lower bound. We can also sample a random value from the space as follows. This might be useful for the random search procedure. A real space is basically a continuous valued interval. We can also specify that the values in this interval should be searched on a log rather than a uniform grid. And then we can also print a random configuration from the search space once again. A categorical search space is one that consists of a discrete set of values from which the searcher should choose one option. The first value listed corresponds to the default setting that will be tried during the first trial of HPO. The categorical space can also be used as a nested search space, where its options themselves may be search spaces. Here we show categorical space A, B, C, where A, B, and C themselves recall were search spaces. When we call A, B, or C.rand and draw a random configuration, we end up with a random one of these search spaces from which we can again sample a configuration. A list space is a type of search space where the searcher will choose one option from each element in the list, where each element would be a search space also in the nested context. And finally, the searcher will construct a list of these choices. This could be useful for something like specifying network architectures, which might require choosing, say, the width of each layer. This is also helpful to avoid having to convert between different data types in your existing code. AutoGluon Searcher will, if your code wants to see a list, AutoGluon Searcher will provide it a list if you just specify that the list search space should be used. In the example below, the first element of this list is an int search space sampled ranging from 0 to 3. The second element is a categorical search space sampled from the choices alpha or beta. We can see a random configuration here corresponds to a integer from this integer search space and a choice from the categorical search space, and these themselves are put together in a list. A dict space is basically the same thing as a list space, just for Python dictionaries instead. In the example below, key 1 here is a categorical space where you have values alpha or beta as the options, and key 2 is an int space. And when we draw a random configuration of this search space, it itself is a dictionary with particular values for these keys. Now we'll talk about how you can insert search spaces into arbitrary Python objects and functions. In particular, you don't really need to modify your existing code much to make it searchable. First, we'll talk about an searchable object with just adding one AutoGluon Python decorator any object returned by a user-defined class can have its constructor arguments turned into searchable hyperparameters. In this example, consider the myObject class here. That would be your existing code that takes in, say, some constructor arguments, name, rank, static value. All we have to do to make it searchable is declare it as an AutoGluon object with this decorator. Inside the decorator, we can also specify a default search space should we choose to, shown here. Now when we instantiate myObject, we can print myObject and note that it's not actually a real object. It's just an AutoGluon object that has not yet been instantiated until we actually ask for a particular configuration of this object when we call rand. Now that we sample the random configuration of this object, we do get a Python object, and it has particular values for its constructor. We can also use AutoGluon to tune any training function. Typically, the training function will contain your script for training a model, but it could be used in other contexts as well. Here we assume that this function takes in various keyword arguments, or args, as its hyperparameters. Usually your training script will evaluate the model somewhere, either at the end of training or after every epoch, and log this information. All you have to do to make this tunable by AutoGluon is add an extra reporter object that AutoGluon provides and also log the performance of your training function in the reporter object as well. Here we show a dummy training function that doesn't do too much. This would be the code that you would have to have originally, where the only difference might be the addition of this reporter object, which we've here made optional so that actually your original function could run regardless. The only difference here is that when the reporter is provided, we record both, say, the epoch information and some performance score, in this case just some dummy score that just sums up 3 arguments. And then all we have to do to make this existing function searchable by AutoGluon is add an AutoGluon.args decorator. Again, we can optionally specify default search spaces for this function if we want to, for the arguments of this function, I should say. Here we show all different kinds that we covered in the early part of the tutorial. Now let's start hyperparameter tuning this custom code. First, we need to create a searcher object. Let's just start with a random searcher. Here we call the searcher on our training function, which recall we had defined the default search space as the combination of all the previous search spaces we previously talked about. When we call searcher.getConfig, the random searcher will return a random configuration from the search space, printed here. For categorical hyperparameters, it will only print the index corresponding to the choice of the discrete options that has been selected. Here's how to run one training job with this hyperparameter configuration specified by the searcher. All we do is we call our training function, again with its args, and we pass in the particular config that we just had from the searcher. And we can see that when we run the training function, recall all the training function did internally was compute some performance as a sum of 3 arguments, and then print out all of its argument values. In this case, you can see all the arguments are actual values, no longer AutoGluon search spaces. Now we can tune the argument values of this training function by creating a scheduler that serially orchestrates 7 training jobs under hyperparameter configurations that will be specified by our existing random searcher. We create this first in, first out sequential scheduler. We pass it the training function that has already been decorated. We pass it the searcher that we want to use. We tell it that it can use 2 CPUs for each trial, and no GPUs in this case. We tell it to run 7 trials here, and we say that the time attribute corresponding, say, to iterative training, maybe epochs or boosting rounds going back to our tabular prediction module, here in this case will be named epoch. Then we call scheduler.run, which will begin launching the training jobs and begin the hyperparameter optimization process. Scheduler.join jobs will aggregate all the results of all the different hyperparameter training jobs. Then we can call scheduler.getBestConfig here, which will print out the best configuration that we've seen so far, as well as getBestReward, which will print out the best achieved performance during the hyperparameter optimization. In this case, we can see there's 7 different hyperparameter configurations that are tried, and we also print out the performance of each one. 1, 2, 3, 4, 5, 6, 7 here. And the best configuration is finally printed at the end, which is shown here, as well as the best performance value. Now that we've demonstrated the basic building blocks that you can use to tune arbitrary pieces of your own code, let's demonstrate their usage in a practical application. Here we'll consider training and hyperparameter tuning a PyTorch neural network on the MNIST image dataset. Oh, that was not supposed to happen. Reset. Now that we've introduced the basic building blocks that can allow you to tune arbitrary pieces of your own code, let's demonstrate their usage in a practical application. Here we'll consider training and hyperparameter tuning a PyTorch neural network on the MNIST image dataset. Let's first import the necessary packages from PyTorch. Here's some example images from the MNIST dataset from each class 0 through 9. We'll apply some standard image transformations to our training and validation images as follows, and then we'll load the datasets which are already built into PyTorch. The main training script is something that looks like the training code you normally write for fitting networks to the MNIST data. If you want to apply AutoGluon to tune your own models, this is where you would put your own training script. You see we specify the device to run on. We have some argument values that will govern training, like the learning rate, weight decay, number of epochs, etc. We have a training loop that operates in one epoch. We have a testing loop that operates in each epoch. We have the accuracy, etc. And so the key difference here is that we need to add this reporter object from AutoGluon into our training code. And whenever we get a validation score, accuracy in this case, we just report it in the reporter as well as wherever else we were storing it before, and we can report it at each epoch in this context, which will allow us to use preemptive schedulers like Hyperband. Let's talk about how you will use AutoGluon for hyperparameter optimization in this context. First, you will have an existing neural network architecture in PyTorch that we will convert to be searchable by AutoGluon. Next, we'll convert the training function to also be searchable by AutoGluon. And finally, we'll create an AutoGluon scheduler and launch the hyperparameter optimization process. First, we need to convert an existing network to have searchable pieces. This is done again by just adding our AutoGluon.object decorator shown here. So here, this class.net code, all of this code would just be existing PyTorch code. In this case, implementing a 2 convolutional layer with some fully connected layers on top of it, convolutional neural network. That's pretty simple. To make this object searchable, all we have to do once again is just add the ag.obj decorator. And here we add it also optionally defining some default search spaces to consider. Here we consider searching over the hidden conv parameter and the hidden FC parameter. The former defines the number of channels in the convolutional layers of the network, and the latter defines the width of the fully connected layers of the network. Now let's make the training function searchable. Recall the training script we had gone over before. All we do now is we write a wrapper around this training script and add the AutoGluon.args decorator. Here we just use a small value for the number of epochs. That's not really a hyperparameter to search. and we just use a small value to make sure things run quickly for your purposes. But in practice, you would obviously want to set this to a much larger value. And here we specify searching over the learning rate and weight decay arguments as real valued hyperparameters that are searched on a log scale. Finally, we create a scheduler. Again, AutoGluon provides two schedulers that you can choose from for HPO, the first in, first out scheduler and the hyperband scheduler. The latter only makes sense if your training job or your training function operates in something like epochs that has some sort of iterative nature such that early termination even makes sense. Each scheduler relies on a searcher to determine which hyperparameter configurations should be tried. The default searcher, if unspecified, simply draws configurations uniformly at random from the search base. That's what we'll do here just by not specifying the searcher. Inside the scheduler, you should specify the resources to use for each training job. Here, 4 CPUs, 1 GPU. The number of trials to run. These are individual training jobs. What attribute corresponds to time or epochs or iterations. In this case, it's called epoch. And what attribute corresponds to the reward or the performance measure. In this case, it's called accuracy. Specifically, we're going to measure validation accuracy here. And this is what this scheduler looks like now that we've created it. And finally, we're ready to launch the hyperparameter optimization process and see what's the best hyperparameter configuration we can find. So we just call scheduler.run and scheduler.joinJobs to collect all the results. Because we specified num trials equals 2, there's only 2 different hyperparameter configurations the scheduler gets to run in this case, because we want to make sure this tutorial will run quickly for you. We can plot the test accuracy achieved over the course of training because we stored it in the reporter after each epoch. And we can plot this now under each hyperparameter configuration that AutoGluon tried out. Here the different hyperparameter configurations are represented in different colors. And you can see that the better configuration is the orange one, shown down here after the 4th epoch. And the validation accuracy achieved under this configuration was 98.9% accuracy. To conclude this tutorial, we'll introduce one last hyperparameter optimization strategy. When tuning neural networks, we often want to early terminate unpromising trials to free up compute resources, and hyperband scheduling can save a lot of wall clock time. However, hyperband relies entirely on randomly sampled configurations. As it completes more training jobs under different hyperparameter configurations, a good AutoML system would ideally learn what sorts of configurations tend to work well and hone in on these promising regions of the search space. This is exactly what's done in Bayesian optimization. Bob is a recent hyperparameter search strategy that combines the early termination strengths of hyperband with the better than random configuration proposals of Bayesian optimization. See the linked paper for more details about Bob. AutoGluon provides an improved asynchronous Bob implementation that can be used to tune your custom models. See this linked paper for details about how Bob was extended asynchronously. Here we create a scheduler to implement the asynchronous Bob search. This scheduler is simply our standard hyperband scheduler, but now we specify its searcher to be a Bayes-opt searcher. The searcher will more cleverly propose configurations based on past experience, while the hyperband scheduler will still monitor training jobs and early terminate those which do not appear promising. When we run the scheduler, it looks the same as the other schedulers. Here again, we're just running it for a very few number of trials to ensure the tutorial runs quickly for you. And we can print out once again the best configuration that was found. For more information, please see these references.